Welcome to MEI Mechanics. We're on the topic of dimensional analysis, and this is video 1.4, Modelling using dimensional analysis. Firstly, just a reminder that when we're dealing with dimensional analysis, we have three different dimensions that we consider in mechanics: mass, length, and time. Now in this video we're going to be looking at the use of dimensional analysis in models, and so the procedure we're going to be following is this. For whatever situation we want to analyze, we're going to suggest a formula that's based on the product of unknown powers of the quantities that we think that the formula should depend on. So these powers, these indices that will apply to the different quantities, we'll call alpha, beta, gamma, and so on. We should include a constant because we don't know the overall size of the thing. We just think that knowing it at one particular point will then allow us to work it out for any other values of the quantities that we have. So we need some constant to deal with that issue. And then what we'll do is, the clever bit is to compare the powers of the various dimensions on both sides of the formula. So as long as we know the dimensions of the thing that we want the formula to tell us, then we'll be able to work out what the values of alpha, beta, and gamma are. So we're going to look at one very nice example of this. We're going to think about the time period of a simple pendulum. Firstly, we need to think about what we think that might depend on. You might want to pause the video and think about this yourself as well. Alright, so if you've had a bit of time to think about that, perhaps you think it might depend on the length of the string, on the mass of the bob, on the strength of the gravity, and maybe on the angle from which it's released. Alright, so we're going to think about those four things initially. However, it's important to note from the outset that this thing here is a little bit different from the other things. Why is that different? It's because angle, as we've seen in the previous video, is dimensionless, and actually this whole process isn't going to work on dimensionless quantities. So we need to sort of put that angle to one side to some extent here, but we will talk about that a little bit as we go through. So as we said then, all we're going to do is we're going to take the things that we think that the period's going to depend on, and we're going to form a product of those things. So we've got three quantities: length, mass, and gravity, that we think could affect the period of the oscillation of the pendulum, and we're going to raise each of those things to an unknown power. And we're going to see if we can use dimensional analysis to work out what those powers are. And we've also got this unknown dimensions constant in there as well. So let's think about the dimensions then. Well, the period, that's the time it takes for one oscillation. So on the left hand side we've got something with dimensions of t. K is dimensionless, so I don't need to worry about that. I've then got L, length to the power of alpha, and mass to the power of beta, and then remembering that g is an acceleration, so think about units of acceleration, meters per second squared, so that's length and then time to the minus 2, the dimensions of acceleration, and then that itself is raised to a power of gamma. So now what we'll do is we'll compare the indices on each side of this structure that we think might represent the formula. So for mass, well, on the left we don't have mass, so on the right mass only appears here, so the only way that that can work is if beta equals 0. What about t? Well, on the left hand side we have t to the power of 1. On the right hand side I've got t to the power of minus 2, and then that is in turn raised to the power of gamma, so we can say that minus 2 gamma equals 1, and from there we can therefore infer that gamma is equal to minus a half. And then for length, well, again, just like mass, we've got no length here. So on the left hand side we've got 0. What power is length raised to on the right hand side? Well, it's alpha there and then gamma there, so it's to the power of alpha plus gamma using rules of indices. So we can say that alpha plus gamma equals 0, and therefore alpha must equal minus gamma, and in other words alpha must be equal to plus 1/2. So what do we conclude from that? Well, we conclude that this time period, if we're right, we'll have a formula like this: k length to the power of a half, because that's where the alpha is, m to the power of 0, in other words not depending on the mass, and g to the power of minus a half. And we can write it in this way. Alright. And it turns out, actually, for a simple pendulum, that that's completely true. As long as the angle of release is relatively small, then that works. All right, and it turns out, and we could obtain this perhaps by doing a measurement, or by doing more detailed mathematical analysis, that constant is equal to 2 pi. So it is important to think about what we've actually done here. We certainly haven't proved that is the formula. You'd need to do further experimentation or further mathematical analysis to confirm that. So the formula could be more complicated. There could be other terms added together, for example, that have the same dimensions but might involve other quantities that we haven't even thought about. Or of course that thing that we've assumed is a constant, that dimensionless k, that might actually be a dimensionless thing that depends on something like, for example, the angle of release. All right, and in fact that is true for large amplitude oscillations. Then this value of the constant would change. So this isn't perfect by any means, but it is still clearly very powerful technique in that it's got something that is exactly like what we know to be true in the simple case, at least. So that concludes video 1.4, modelling using dimensional analysis, and concludes the topic of dimensional analysis.